have a bunch of stuff that we're going to be covering here in the second magnetism and electrostatic session, where we're essentially going to be dealing with just magnetism. We're going to talk about magnetism, application of magnets, application of right-hand rule and how magnets influence other charges, and then do a bunch of practice problems. Because the best way to really get a feel for some of this is really just putting it into play, seeing the sort of MCAT problems you're going to see on test day, and making sure that you have that on lockdown. As I talked about in the first electrostatics and magnetism session, a lot of the application comes by relationships and by understanding how one thing influences another thing. Not necessarily simply memorizing the formulas, but understanding how we have the interactions. So let's jump in and take a look. First of all, we are going to be running down through magnets and magnetic forces and magnetic fields. We are going to talk about the application of electrostatics and really try out some MCAT-style passages. Specifically, at least one passage at the end, and then we'll have one more for you to do for homework. Let's jump in, though, first with magnetic field and force. Now, if I had a unit that I was going to have named after myself, I think I would probably do the Tesla squared. Because a Tesla is such a crazy unit. Nikola Tesla was an insane genius. Look at this unit. It is a force time per distance charge. Who came up with this? It would be the Schwartz, I think, or the Eli. Either one of those, Hannah. And it would be a Tesla squared. So it'd be a Newton squared, second squared, meter per meter squared, Coulomb squared. I think that would just be crazy. Because again, look at these units labeled together here. This is ridiculous. Magnetic field is some sort of interaction of force over a particular amount of time at a distance on a charge. That's what Newton second per meter Coulomb is telling us. That's awesome as a unit. Now, what that unit is actually doing, in sort of a neat way, is it's summing up the entire formula in one place for you. So if I was asked about, what is an electric field doing? Electric field is pushing on a charge, the point charge. What is a magnetic field doing? It's pushing on a moving charge. That's pretty cool. And the amount of that charge moving, the current, which is our I here in this formula, is proportional to the amount of magnetic field. So B proportional to I in the formula here in the center of the screen. But it's also inversely proportional to distance. The further away I go from a magnetic field, the more it drops off. That's a Bellany's question. I think you should memorize all of the units for physics and for Gen Chem, just to be sure, because what the units actually help you do is memorize the formulas in sort of a reverse way. Now remember, there are way fewer units than there are formulas. So it is not like I'm saying memorize all these extra formulas, but a great example of this, of how a formula can give you actually what it is based on units, is let's think about force. Right? Force, we know, is a Newton. And a Newton is a kilogram meter per second squared. Now, kilogram meter per second squared, that looks like I've got a mass here, and I've got acceleration. So F equals ma? That sound familiar? I mean, the units have told me that's what the formula should be, but this looks pretty familiar. That's why we should memorize units, is because units can actually help you derive relationships between variables. Boom! Newton's second law, absolutely right, Nadine, or as we like to call it in the hood, Newton 2. Now, as far as the application here for that force, right, the force here from the center, the force equals the magnetic field equals the current per radius, that actually segues quite nicely into our wraparound rule. Suppose I have, like my pen here is apparently a current-carrying wire, and it's pointing straight up towards the ceiling. What we use is the wraparound rule to determine where that magnetic field would be pushing on a moving charge. So we take your hand, your right hand, take it right now, you have one I think, take your right hand and point your thumb straight at the ceiling, because your thumb is current, right? Current is I am thumbs up, so right hand is thumbs up pointing towards the ceiling, and your fingers, if you're trying to grab this wire, should curl around, exactly right, clockwise from the bottom if you're looking up at it, or from the top counterclockwise, where your fingers go into the screen on the right, if you're trying to grab this right now in your computer monitor, and come back out of the screen on the left. So technically this would be counterclockwise from the top, is how we would describe this particular motion. Just to be clear, Bellany, usually they tell us clockwise from the top or counterclockwise from the top because we're always looking down a wire. But if they had this reverse, if it was pointing at the bottom of the screen, again, you would have to have that definition, whether you're looking at it from the top or the bottom. But your hand, your right hand, should now be curling around that wire, and that's showing you the direction that a moving charge would be forced if a moving charge was nearby. Now, bonus question, does this mean that the wire is getting pushed in and pushed out in those directions itself? No way. Because then if you were charging your computer, it has electrons flowing through it, it has current, your wire would now be wiggling around and putting force on itself? No, just a charge moving by. Exactly right, Eva. Bonus question on top of the bonus question. What if I put a point charge and I set it down in place along one of those x's? What's going to happen to a point charge not moving? I love this bonus question because it's a magnetic field. Magnetic field only affects moving charges. This is the sort of thing I've seen the MCAT bring up in questions before. An electric field moves any charge. A magnetic field, write this down, requires the other charge to be moving. If it's not moving, magnetic field doesn't play with it. We're actually going to see this come up in a question that I'm saving for later. But this is that kind of bonus question where the MCAT could give us a field, let's say in space, a magnetic field and an electric field, let's say, in different places in an apparatus, and we'd have to have something moving or something not moving. They could give us a really complicated system and ask us those types of questions. Yes, exactly, Nadine. Right? We can't just have a ping pong ball moving through the system. It has to be a charged thing. So a proton or an electron are the classic examples, but a charged ion could do the same thing as long as it has a net charge. Now again, what Dama is explaining is important, the moving thing. So let's go into a little more detail about this moving thing. Suppose I have a moving charge and I already have a magnetic field. Now I'm going to be using the right hand rule. And if you've been doing this right hand rule with the 3 fingers and it's worked for you, great, use that. But if you don't already have a right hand rule that you love, here's what we're going to learn. Take your right hand. Now remember, you are awesome, right? I am cool, I am awesome, I am thumbs up. So your thumb is current, because current is I. Fingers are like field lines. You have many fingers, you have many field lines, fingers, field. So your fingers point in the direction of whatever the magnetic field is pointing. Palm is for push. You can push with your palm, you push and create a force. So the force is always the direction your palm is facing. Cool? Let's do this first problem on the left. Suppose I have a proton, positive charge, and it's pointing straight up towards the ceiling. Take your right hand, put your thumb at the ceiling. Fingers should be pointing into your computer monitor because that's where it shows the field lines. Field lines are fingers pointing directly into your monitor screen. Where is your palm, the force, pushing right now? Better be pushing directly to the left. Nicely done. Absolutely. Now, at this point, we've been using the right-hand rule. It got us forces pushing to the left because we're tracking the positive charge. Positive charge is current. We're good. On the right, we've got an electron. Now, we know by default, the electron's got to be going the other direction. It's the opposite charge. Should I use a left-hand rule? Should I flip over my right-hand rule? Here's a simple answer. Right, Brandon. No, use your right-hand rule, do everything the same, and at the very end, whatever answer you get, just make it exactly the opposite. Because it's an electron. That's it. Don't do left-hand rule. Don't complicate things. Thumb is pointing straight up. Fingers are pointing into the screen. Your hand is pointing to the left. Uh-oh, it's an electron. Make it to the right. That's it. So again, don't make it overly complicated. Keep it simple. Keep it as one right-hand rule so you don't have to go crazy. Done. Now there are some formulas up here that I glossed over in order to jump in with specifically the right-hand rule. Notice the formulas at the top should look pretty similar to formulas that you will see in your intro physics material. These look pretty similar to one specific physics concept. You're right, Brandon, cross products from torque. Brandon, Isaac, Nadine, love it, absolutely. Whenever we have a sine theta relationship, that means we have to be at 90 degrees to have the optimal amount of force. So when theta is 0, we have our full formula, all of the force being applied. When it's 0 or 180, we got nothing. So what this means is my proton on the left is pointing straight up, then it's going to be forced to the left. So it's going to curve around like this. Now at that point, it's pointing directly to the left. Hold on, let's do it again. Double right-hand rule. It's really the same right-hand rule. Point your thumb now directly to the left. Point your fingertips into the screen. Now where is your palm pointing? Yeah, pointing straight down. Exactly right. So now it's going to be forced down. Okay, now, yoga time. Take your thumb, point it into your lap. Take your fingertips, point it directly into your computer screen. Where is your palm pointing now? You look a little ridiculous in the library. Let's be honest. You look a little weird. But yes, you are pointing directly to the right. And then if you're going to the right, it'll point back up. And you've got this nice circle, as Nadine points out. Well, this is because we're in a uniform magnetic field. And if we're a moving charge, we're constantly experiencing this force. So we're cycling around in a circle in that direction. And of course, an electron would have the opposite circle. It would circle around to the right. Groovy. Now, this is the sort of thing the MCAT could ask you. Not just what happens once as we have a right-hand rule, but maybe as it keeps going, keeps going, keeps going, you should form this nice circle. Sweet. Now let's go a little bit further here and talk about the application of that circle. We have circular motion. Well, if we've got a force, and we know it's QBB, and we know we're in a circle, then we know we have the centripetal force, mv squared over r. So you could actually make those two equal to each other. And this is the sort of thing that whenever you see an MCAT question that seems like it's dealing with two concepts at once, you should immediately try and remember, what are the formulas that I can relate together? Force is often something you can relate across multiple concepts. So multiple concepts being force across electrostatics, force across circular motion, force across mechanics. All of these things can come back together. So force is one. The other one that you're most likely to see formulas cross over is energy. So really expect to see energy like mv squared equaling out to some sort of electrostatic energy, equaling out to some sort of circuit energy. These are the sort of crossover concepts we should see a lot. Now, as far as that force goes, though, let's talk about a current that's maybe going up on a wire from A. That means that on the right-hand side of this wire, the magnetic field points into the screen. And on the left-hand side, it points out of the screen. This is like you take your right hand and you're grabbing that wire again. This is the wrap-around rule. If we had another wire, though, going the opposite direction, pointing straight down, then you can take your right hand, wrap around rule, grab that wire, it goes into the screen, and it goes out of the screen proportionally, but on the flip side. What do you notice if we ever had two wires going opposite directions right next to each other? They both have an into the screen magnetic field in the middle, and on the outsides, you're right, Chris, on the outsides they cancel out. Well, this sounds awesome, right? This would be a way that if, let's say, you were trying to charge your computer and you didn't want that wire to be influencing other electronics, what could you do? I guess you could have charges flowing into your computer on one side, and then you could have charges flowing back, exactly right, Chris, the opposite way. And that would give you a perfectly canceled magnetic field wire. Now, why would that be a terrible way to run a charging cable? If we have to run current equally in both directions in order to insulate perfectly the magnetic field from itself. Then there's no net charging. Exactly right. Then we're forcing stuff to go one way and the other way the same amount. Then there's no net going into my phone or my computer. So that would be bad. That's why what James put in here makes a lot more sense. If we're only going one direction, if we don't have this B, then we have to insulate this wire because it is creating a net magnetic field. Cool. Now just to be clear, the force on A, this wire, because it's a moving wire, comes from B. The force on B, because it's now a moving charge and it's in A's field, comes from A. This should have an A on it. I don't know why it says B. Because A is the field that's influencing B's charges. So these two things are influencing each other, right? It's like force of one on the other equals force of the other on one. Yeah, exactly. ILB is the formula. Exactly right, Nadine. But specifically, just to be clear, this is A's color. So A is influencing B. And of course, on the flip side, B, which is B's B, is this one, which is influencing A. Because again, they're charges moving through space. Anytime we have charges moving through space, we think that means magnetic field influence. So let's go one step further. Let's talk about a problem that gets about as complicated as the MCAT would ever give you on test day. An apparatus that has an electric field, a charge moving through it, and we need another magnetic field to balance something out. This is about as complicated as you would ever see, so I do want to give you a chance to actually try this one out on your own. See if you can spot the connection they want you to make. Now again, no hints for your fellow classmates per se, but if you do spot the important point, the important word from the question, let us know down here in chat. But I'll let you try it by yourself first. Now, I did give you about 40 seconds. That's about the amount of time on testing that you would want to spend on any one problem, either an easy problem or a hard problem for that matter. Maybe you've got a buffer. Maybe this problem comes up near the end and you've saved some time. You've answered a bunch of 20-second problems leading up to it. Great. But the key piece here is what Hannah pointed out. Nicely done. Undeflected is the most important thing. So let's talk it through piece by piece. Let's suppose that we didn't have any magnetic field. If we didn't have any magnetic field and we have a positive charge moving into a space that has an electric field, what's going to happen to a positive charge as it's moving through an electric field? Yeah, Nadine's got the most vague answer, which is the one I'm looking for here first. But Brandon and Bellany, you've got my follow-up question. It's going to feel a force. Now, the more specific question that I was going to follow it up with is exactly right, Hannah. Nice connection. The positive charge doesn't want to be anywhere near the other positives, and it wants to get down towards the negatives. So this is going to curve, at the very least, down. Now, how steeply it curves down depends on the magnitude of that electric field, but no matter what, it's going to curve down in our screen. So what we actually want to do then is we'd really like it if that got pushed back up, right? Wait a sec. Pushed back up. Does that mean we want A up, as about a quarter of us had answered? Do we want out, as about a third of us have answered? We've got a whole spread among the answer choices. So hold on. You know what we could do? We want to know the force from a magnetic field. I got a right hand. Point your thumb directly to the right. That's where the positive charge is moving. Now, point your palm straight up, because that's where you want the force to be. Where are your fingertips pointing now? should be pointing into the computer screen. Done. We want the force to point straight up to cancel out the electric. And it's going to the right, so thumb points to the right. The only possible way to make this happen is if the magnetic field is pointing into the page. Answer choice C. Now again, remember, fingers are magnetic field, I is positive charge current flow, and then palm is push. Now to Bellany's question, let's try it, right? Let's try it to prove why it doesn't work. Take your thumb, point it directly to the right, okay? Now point your fingers out of your computer screen, so facing back towards you. Where is your palm pointing now? Pointing down. Exactly right, Michelle, right? Adnan. If you take your thumb, point it directly to the right, take your fingertips, point them back at yourself, like so, your palm should be pointing straight down. But straight down is the way that it's already being pushed from the electric field. We need a new magnetic field that pushes back against it. That's because of the one word, which is that it has to go through undeflected. Exactly right, Isaac. And this is that careful reading. Remember, I told you before we began this problem, this is about the highest difficulty question the MCAT would ever give you, because we're combining both electric and magnetic and a moving charge. And if you got this one, give yourself a pat on the back. And if you missed it, don't feel bad, but try and assuage the issue. What did you miss it for? Was it because you didn't point your thumb in the right direction? Was it because your field lines were not tracking magnetic? You were accidentally putting them where the electric was? If you can fine-tune that, exactly, Nadine, like confusing electric magnetic, that's exactly the sort of thing that means you can get that next question. Doesn't really matter whether you got this one right or not, let's be honest. Test day is the one we care about. And if you've got follow-up questions about this one, as always, hit us up in the Q&A. I know that Dom is ready to answer any questions that come through there. He's already answered a few great ones. So feel free to toss some follow-ups in there to Dom. Now, for the next chunk of class, I want to segue into more problems, because it's not so much that any of these given problems is necessarily trickier than another. It's that this particular application of the problems, which is the real issue that we're trying to resolve. We're really trying to get that connection to what is the issue at hand. Now, what we've got is two different passages. One of the passages, the second one, I think we're going to assign for homework. There's one problem out of it, though, that I might still do. But the reason I'm going to assign the second passage for homework is because it deals with electrostatics and magnetism, but the formulas you actually use are from kinematics. So in order to figure out what's happening, you need to know electrostatics. But in order to solve, you actually need things like the VAX formula, TAX formula, simple kinematics formulas. So instead, we're going to pay a little bit more attention to this first passage and really dig into it. Show you the way that you can tackle this anytime you saw it again. Let's jump in, though. What I want you to do is actually do some outlining. So down here in the chat, I'm going to give you about a minute and a half to read everything that's here on screen, just this first chunk of stuff, and then give me an outline that you would jot down on your scratch sheet for this information on screen alone. Go for it. Take about a minute and a half. All right, I gave a little bit of extra time to do your outline because I know outlining takes a lot of effort for a lot of us. I know even for me, I've been going down through and taking all of the full-length exams that you have on your syllabus to make sure that I'm really prepped for all the material you could see by test day. And I've been taking the full-length exams, and even I have to force myself. Jot down something for the outline. It is going to come back and help me. It's going to make researching easier later. You just have to force yourself to do it. That way it gives you that net benefit later when you actually can use the outline. So for paragraph 1, we could jot something down about the fact that we actually have that ionization. So paragraph 1, we've got a little bit of an outline here, maybe dealing with the fact that we have the atoms ionized. So we know we're going to have a net positive down there in that left-hand side of that figure for the isotope spectrometer. And we've got some more information that tells us that we've got these isotopes have different velocities and arrive at the detector at different times or different places. This is something we would probably jot down relatively simply, like how Isaac put in here, different velocities at the end, or different in-between plates, as Brandon points out. We're accelerating, and then we have something related to velocity for Michelle, because we don't necessarily know the relationship yet. We could figure it out. We can actually plug into the equation they give us here in the middle, but how come nobody wrote down the equation? It's not a trick question. How come nobody wrote it down? It's there. Sure, Bellany, right, Brandon? And how often is the MCAT going to give you an equation in the middle of the passage and then give you 3 or 4 questions that use that equation so you don't have to do any extra memorization to get them right? We wish. We wish they would give us that equation and then nothing else that we'd have to do. That'd be great. No, super unlikely. Instead, if you see an equation in a passage, expect you might get 1 question that uses that equation. On tops. If it was a really long equation with a bunch of variables, maybe 2. That's it. Expect if you see an equation, that's maybe 1 point. Maybe even less, though, because maybe that same question that would have used this equation, we could actually still have gotten that point without the equation in the first place. And Nadine, again, we do want to try and use it if they give us that question, but oftentimes we can still get to the answer based off of that question anyway with a different formula. In fact, we're going to see how we could do that in this passage. Before we do, though, I want you to do one more thing here. Tell me what you would jot down for your outline for figure 2. I loved what you put in here for the outline for the first chunk. Nice, concise, simple. But for this one, I might be expecting something a little bit more. Tell me what you would have to jot down for your outline for this chunk that I just put on screen. Love it. Love it. Now again, for the outline, I notice that we've got some good outlines here that deal with the relationship. And that's always, whenever we see a figure that shows us results, whenever we see a table, whenever we see a graph, look for outliers or look for patterns. So I love that Hannah put in here, the highest one is number 4, and the furthest one is number 5. Because that's that sort of outlier that looks weird, that we're probably going to get a question about. Why is 5 so far away? I expect we're going to get something about that. Similarly, I like that Bellany and James are putting here this ratio, right? The mass and the charge are the 2 things that determine how far out it goes. Now, it does give us some information. It says the location depends on those 2, but the formula from a second ago actually helps define that, right? Because the velocity is here on the left, and then the charge is on the right. So there must be this kind of direct proportionality between the velocity and the charge, and mass is on the left, so mass and velocity must be inverse relationships. So really, Once we knew that mass and charge were related from this paragraph, I would probably encourage you to jot down something like this, that the distance, or the velocity in this case, is proportional to the charge, and that the velocity is inversely proportional to the mass. Because that's the sort of relationship that this formula is actually giving you. This is what some of the best test takers do. When they get a formula or when they get a relationship, they jot down what we actually know about it. If the charge was held constant and the voltage was held constant, then mass and velocity are inverse, like I have here at the top. Now again, we skimmed the formula on purpose, Michelle. That was the right task to take. Skim it because we don't know if it's going to be important. But as soon as they gave us this, the location depends on mass and charge, boom, all of a sudden that formula became way more important to us. Because now we know there's going to be some sort of relationship question. Because they specifically haven't told us the relationship, we're going to be asked about it, for sure. And the fact that peak 5 is so far away must mean it has a really low mass or a really low charge, something like that. And the fact that peaks 1 and 2 are so close must mean it has a really high charge or a really heavy mass. Right? This is the relationships that we might get asked about. Yes, exactly, Nadia. Exactly, really high mass. Yep. Now again, yes, exactly, Isaac. This gives us a potential relationship. Now I don't know yet, Michelle, I mean I do actually, but we don't know yet from the passage why peak 4 is so high. We don't have any relationship about that, right? So we expect, we don't know why it's that high. Maybe that's going to be a future question, right? If peak 4 is this high because of XYZ, what does that tell you about peak 2 or peak 5? This is the sort of stuff that as soon as you see anomalies or outliers or patterns, immediately latch onto that. That's that future question. Now, let's jump in and actually do some of these because I know we've got plenty of time here to tackle them, and you're going to see how the prediction we just made, thinking about what's most important, thinking about what's going to come up, is going to immediately give us points. So, first of all, this is a pseudo-discrete. This is a question where we really didn't need anything from the passage, and we can try and grab up this point. This is the sort of thing that you'd want to put on a flashcard if you don't already know this, or again, go through and look back over the first couple of chapters of the physics notes, because this is where we talk about the numbers. But we could probably get it down to 50-50. Sure, Nadine. And your classmates, I think, are in the same boat. We're at about a 50-50 split between A and C. We don't generally track just neurons, just neutrons, excuse me, so it's not B. And we generally don't track the difference between protons and neutrons, which is D. Those are neither of those two values that we would ever expect to see. Now, the A and the Z thing, exactly, Nadine, the A on top is the mass. The Z on bottom is the number, where atomic number means number of protons. So the mass is the overall weight. The overall weight really only depends on protons and neutrons. Electrons don't really have any mass as far as we're concerned. So C, as people are shifting to, is the one that we're looking for. The atomic number should never change. The atomic number defines that element. The mass number could be part of isotopes, could be different values, depending on how many neutrons we can rip off. Exactly right, Michelle. Never changes for that atom. So lithium will always have 4 protons. Sorry, 3. Lithium will always have 3 protons. What world am I living in? Hydrogen, helium, lithium. 3. Right, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, etc., etc., etc. We can go through the whole list, but lithium better be 3 every time. So the number of protons plus neutrons is our 6th value. It's always the one on top. It's always the one that could change if we had an isotope. How about this one? If we have doubly ionized lithium isotopes, hold on a second. Here's our chart. We know something from this chart. Let's not forget the fact that we're coming into this with some knowledge base. 3 and 4 are lithium singly plus. They're telling us that we've got doubly ionized. Before we get into the nitty-gritty, I want you to do some critical thinking. Help me avoid making any mistakes here. What could I get rid of? Because I know it's not doubly ionized lithium. Right, exactly, Chris. It's got to be 1 or 2 or 5 in there, right? Because those are the only things that we know are different than the singly ionized case. Huh. Did I just maybe blow your mind on this question? There is only one answer that has a 1 or a 2 or a 5. Got to be answer choice D. That's it. We're done. It's a 10-second problem. You will find these on test day. By doing quick elimination, we didn't have to do whether the doubly charge is going to make it higher velocity or lower velocity. No, this is a simple elimination problem. It can't be any answer choice that has a 3 or a 4, because a 3 or a 4 is the singly charged. Boom, A is gone, B is gone, C is gone, done. If you hit a problem like this on test day, don't freak out. We can get it right. We can be fast. Now you could check your work. I understand. You could mark it. You could come back to it and check your work. But let's think about the relationships that I mentioned earlier. We had that 1/2 v squared equals qv thing, right? And that thing in there, that relationship, is what we put down earlier. V proportional to charge. Right? As V goes up, Q goes up. So we'd expect, as this charge increases, we're double charged, velocity increases, it's going more fast. So if it's going faster, the time should be lower. Yeah, we could work down through it conceptually. We could get to answer choice D anyway. But that's for the other person sitting next to you, who's going to spend a minute on this problem. Whereas you just hit it in 15 seconds, dropped the mic, walked away. That's the sort of thing we'd love to do on test day. Grab up a handful of 15, 20-second problems, and then have the extra time to spend on the harder ones where you don't see the trick. Absolutely. There are going to be ones where we don't spot the trick, we spend extra time on, sure. But if you're always looking for that silver lining and that shortcut, you can spot it. If you're not looking, we're never going to find it. Now, speaking of looking for those kind of shortcuts and tricks, let's look at number 4, because it's clearly asking us about some sort of orientation for a field, and we've got a lot of ways that we can play with fields. So, if we've got a field here between the plates, and we want the ions to be accelerated correctly, there's one word that's important from that question stem. It's going to be super helpful for us to figure out where the field points. Direction is good. We want to know the direction, for sure. In the correct direction. Okay, now let's start there. I argued correct direction is first and foremost the piece we need to know. Where do we want it to go? Now, we wanted to get to the detector over here, so we want it to go to the right. Cool. Now there's a second most important word in here that would immediately change the answer if it was a different word. Electric field. Nicely done, Brandon, Nadine. We're getting to be experts up in here. I love this because you're picking up the little clues that the MCAT is dropping for us. We're detectives. We're looking for those little pieces. Okay, electric field pushes a positive charge in the direction of the field. So we want it to go to the right. That's the correct direction. And we're moving positive ions. Well, an electric field moves positive ions in the direction of the field. So it must be what 2/3 of us have already answered in with. It must be D. It's pointing towards the right. That's where it should go. Now, if you answered one of the other ones, you might have accidentally been doing like the right-hand rule stuff. Right-hand rule is for moving charges in a magnetic field. But let me ask you this as a bonus question. Bonus question. What if this charge we knew was moving in some other direction? It was already moving, let's say, straight up. This is a total bonus question. It has nothing related to the original question at hand. Suppose the charge, this positive charge, is moving straight up, and we wanted a magnetic field in order to get it to go to the right. Where would the field have to be pointing? Out of the page. Nadine, Isaac, James, Chris, super fast responses. I love this. Everyone be on the same page here for a second. Point your thumb straight up towards the ceiling, and then your palm has to go to the right. Now this is yoga again, right? But point your palm to the right and your thumb up towards the screen. Your fingertips should be pointing back out at you. And exactly, Nadine. In order for it to have been a magnetic field, which is the bonus question I'm asking, we would need to have it moving in the first place, because we have to be able to direct the force. Now I'm going to clear this back off because, of course, this question didn't actually ask for magnetic, and that was the whole point. It just asked us for electric. Because it asked us for electric, we got the quick point, no extra work, no extra default stuff that we had to play around with. And you know what, Marty? How about if I do not this one, but how about if I do another question? That way we have even one more chance to try this out. Groovy. Suppose I've got a detector up here, and I have a positive charge moving directly to the right. What kind of magnetic field do I have to put on this thing in order to get it to go up towards the detector? Nice. Fast. Isaac, Nadine, I love it. And again, just so we're clear, take your thumb, point it directly to the right. You want your palm to be pointing straight up because that's where the detector is. That's where we have to force this charge to go. If your palm is directly to the right and your fingertips are into the screen, if your thumb is to the right, your palm is up, then your fingertips are going into the screen. Exactly right. So magnetic field would have to be in, which is represented by X's, which will enable us to have a force pointing straight up. Right. Now again, as Dom put here in chat earlier, remember the most important difference between magnetic field and electric field is the electric field can put force on an immobile charge. So this really has to be an electric field. It couldn't even possibly be a magnetic field because it's not moving yet. Correct, James. Magnetic field would have to be moving in order for us to see any sort of net force on it. That's why I had to give you that extra bonus question where I had to make it moving and then I had to have it in a direction because otherwise we couldn't have any force on it. Now, let's do another one with that diagram to get into a little bit more depth. Suppose instead they did something fancy. They decreased the voltage. Oh, dear. Some sort of relationship between voltage and answered choices deal with like times. So maybe we have to relate this to velocities. Gosh, I wish I had some sort of relationship between velocities and charges that I could... Oh, the equation! Exactly right, Brandon. This is the sort of thing on test day I find myself doing repeatedly. I forget that there was an equation because I'm so used to just coming up with the equation on my own and memorizing them. Yeah, if you see something where you're not familiar with the relationship, equation. There must have been something in there, some sort of hint. Groovy. Here's our relationship. Now again, we actually broke this down already in our outline if we were paying really close attention the first time through, and we wrote down something like velocity proportional to voltage, velocity proportional to charge, velocity inversely proportional to mass. Something like this. We probably had something around these three formulas kind of jotted down. And usually, just for clarity, if I'm ever jotting down my notes, I usually put a little arrow over the V that is my velocity, because my velocity and my volume, or my velocity and my voltage, or any of the other V terms, tend to start to look pretty close to each other. So just for your shorthand, the pro tip for making my own flashcards for years, have some difference between voltage, velocity, and any of the other V terms like volume. Now, we don't even need these relationships. I'll leave them down here in the bottom. Sure, Nadine, you could jot it down as VEL, whatever saves you time, shorthand. But no matter what, we've decreased velocity. Why do I know this? Because we decreased voltage. Everything else has stayed the same. So if I've decreased velocity, then, gosh, none of the answer choices say decreased velocity. Gosh, that would have been great. But if I'm going at a shorter velocity, smaller velocity, then it must take longer to get to that point. Oh, absolutely, Brandon. Yeah, Nadine. Well, then we're looking for an answer choice. As over 80% of your classmates have already answered, that matches up with it's going to have more time. And you may already know this, but over 80% means star time. Over 90% is Black Star of Doom, Nadine. We're close. We're so close. We were at 85%, right there at that cusp. But I don't give out black stars until we get that 90% mark. I think we can still do it. I think we can do it maybe on this question. I'll let you work on this one. Take about 30 seconds. Think about the formula we have, the relationships we had from a second ago, and let's see if we can get Black Star of Doom. And you're allowed to give each other some hints in chat, but I don't want any letters. Don't overtly give out the answer. Go for it. All right, let's take a look. I think there are a few people in here that have latched onto the trick here. Tell me, in the question, they gave us one hint, actually, already. What's the one hint they already told us before we go any further? Assuming equal masses. Okay, now again, we had a relationship, right? Velocity is proportional to 1 over mass. So far they're telling us that, hey, the masses are the same. Well, okay, then the velocity hasn't changed yet. So no difference in timing. All right. What was one of my other relationships? I had velocity is proportional to voltage. That was one. And I also had velocity is proportional to charge. Okay, interesting. I have helium plus and hydrogen plus. So it's proportional to mass, and they're the same mass. It's proportional to charge, and they're the same charge. We're right there at the cusp. We're right at that 80% mark. So you're going to get a star no matter what. But there's no difference in voltage. There's no oh, I didn't tell you the answer yet. But everybody just changed their answer to C. All at once. I think you deserve a black star. I didn't tell you the answer. I didn't give it away. But everybody did change their answers all at once to answer choice C, which is absolutely the correct answer we're looking for here. Awesome. That is Black Star of Doom. Black Star of Doom. Nicely done. Now again, there are some distractors in here. We always get caught up on things like helium has more protons than hydrogen. Yeah, but that's overthinking the question. Because the question just wants to know what is the charge of the ion. Well, they're both +1 charges. And they want to know what is the mass of the ion. Well, they're both the same mass, it tells us. Okay, then they're both the same mass and they're both the same charge. Then that's it. Done. There's nothing in here about voltage, so you can get rid of that one. The only two possible relationships cancel out. And exactly right, Michelle. That's the sort of thing a lot of us fall into. But just to be clear, the right answer has to be C for Cobra. It is a positive and a positive, same charge, and a 3 and a 3, same weight. There was nothing in here in the question stem or the relationship that had anything to do with number of neutrons or number of protons. It was just overall weight or overall charge. So nicely done. Check out that black star of doom. That's what AAMC will look like when we crush questions like this. Look at how grumpy it is. At this point, I told you I would do the second passage for homework, but I still want to do at least one question from it. Because I want to point out that even in a passage that might look tough or might look long or might have something like a crazy apparatus, that we can still get those points. So we're going to do one question out of that, but before we do, let's do one more question from this one. Suppose we got asked about peak 5. Did we expect to get asked about peak 5? Was that something we predicted we would see? Absolutely. It was our outlier. We knew we were going to get this question. Okay, now, assume this is from a different atom. What could we say if we know it's singly ionized? Oh, what a beautiful question. Because they're giving us what relationship we should be caring about. There's only one relationship left, and it's weight. Exactly right, Brandon. Because if it's singly ionized, then it matches up with the singly ionized species we already have in 3 and 4. So it's got to have a difference in weight. Well, if it's got a difference in weight, do we want it to be heavier or lighter? Want it to be heavier, James says. Brandon already said heavier. Melanie, heavier. Okay, yeah, it must be heavier because it's taking longer to hit. Right? Heavier, takes longer, lower velocity. Okay, so then get rid of the fewer and the fewer, answer choice D. Get rid of any answer choice that doesn't tell us for sure heavier. I'm being vague about this because I want you to help me out here. There's two answer choices that are too vague, that don't actually tell me for sure we're dealing with heavier. Yeah, it's B and C. Exactly right, James, Hannah, Janet. We can't be changing the protons and lowering the neutrons because we don't know how many in B. Similarly with C, actually, we can't change the protons and add neutrons without knowing how many. If one's going up, the other's going down, it might be equaling back out. No, we want them to, as a net, for sure be heavier. The only answer choice that guarantees we're heavier is answer choice A. More protons and neutrons would mean for sure it is a heavier element. Had to be a change in protons, though, no matter what, right? Because we have to be going to a new atomic species. So we could have gotten it down maybe to A and B right off the bat, but we have to guarantee it's heavier. That's why it's got to be answer choice A. It has to be overall, overtly heavier. Nicely done. Now, I did want to say one more thing before we close out for the night, and that's, this is the passage we're assigning for homework. It looks kind of tedious as an apparatus, has a bunch of text here, there's some relationships, maybe a circuit even could come into play. There's something about rails producing a magnetic field, the railgun is producing forces. We could see a lot of questions about this passage, and you do in the homework assignments. But right off the bat, the very first question is one that I know you can answer. So let me give you a chance, one last black star of doom before we close up for the night. Which of these is showing us what we would expect for current flowing through a wire producing a magnetic field? Go ahead and poll in when you think you've got it. The last one of the day. We're done after this. Got almost everybody voting in this one. Can't be A. Nobody voted for that because we don't have a straight field. That would be if we had something else happening here, like an electric field. It can't be C. It's not the straight field in the other direction. If we've got a current, remember what you can do with a current flowing through a wire? Wrap around rule. You can grab it and see the circular motion around the current from the field. That is absolutely answer choice B. Boom! Nicely done. Final black star adieu, and we are, of course, finished out for tonight's session exactly on time. If there's anything else I can personally help you answer about electrostatics, about magnetism, about dealing with advanced circuits, do not hesitate to let me know. I will stay for as long as I need.